In this video, we're going to cover section 4.7 on cycloalkanes. And as you recall from previous discussions, cycloalkanes are cyclic systems. They're cyclic or ring systems. And in particular, we're going to be looking at the relative conformations of these ring systems. And one thing that we observe is that there is angle strain associated with these ring systems as the angles between these carbon-carbon bonds deviate from the preferred angle of 109.5 degrees. So if we look at the relative heats of combustion for these ring systems, we can get a better picture of the relative stability of these systems as we go from a small ring size to a larger sized ring. And so this is a typical way to measure the relative energy of a molecule, but in this case of different cycloalkanes, is that we will combust them, we'll burn them, and look at how much energy is released during that combustion. And so you can see that clearly the three-membered ring, cyclopropane, has some of the highest energy or highest heats of combustion being released per CH2 group. And so this is reflected in that significant decrease in angle between the two carbon-carbon bonds in that ring system. As we go to a 4-carbon system, there's a drop in that energy, but still significant energy associated with the reduction in angle. Because at the cyclobutane, we still have that angle of about 90 degrees, which is still significantly lower than the ideal tetrahedral of 109.5. As we go to the cyclopentane example, we see a significant reduction in the heat of combustion, and that is a result of, again, a reduced amount of angle strain, as the angle in cyclopentane is becoming more like the ideal that we observe for an sp3 hybridized center with 109.5. And interestingly, the lowest energy associated with the ring systems is the cyclohexane example. And so in many ways, the cyclohexane represents the closest to the ideal tetrahedral for an sp3 hybridized carbon center. And one other thing that we have to be cognizant of is that in addition to the angle strain that we observe with these smaller ring systems, even as we go to the larger ring systems, there can be torsional strain associated with the overlap of neighboring carbon-hydrogen bonds. And so in some instances, torsional strain can be quite significant even when angle strain is somewhat or significantly reduced. So when we go to the larger ring systems, we would expect that angle strain would be less of an issue, and primarily the strain associated with these larger systems tends to be as a result of torsional strain being experienced between neighboring carbon-hydrogen bonds, covalent bonds, the electrons in those bonds. Nonetheless, we see a significant decrease in the heats of combustion as we go from 3 to 6 carbons in the ring. And then afterwards, there's a slight increase for ring systems up to 11, followed by yet another decrease as we go to rings larger than that. But there is something special about the 6-carbon system, the cyclohexane ring system. And so we'll discuss more about cyclohexane and its stability in a few moments. But before we look at the cyclohexane, let's look at some of the small ring systems so we can appreciate how angle and torsional strain affect the overall energy of these molecules. So in cyclopropane, the angles are so severely reduced relative to the tetrahedral, the 109.5 angle, that we have significant angle strain. And even when you look at the sp3 hybrid orbitals that are involved in the sigma bond between the two carbons, you can see that we can't have that sideways overlap due to the angle strain associated with this system. And in many instances, we refer to these bonds as banana bonds because of the curved nature of the interaction between these orbitals. So again, recalling our valence bond orbital theory, the strength of a bond is really reflected in its ability to overlap with another orbital. And so if the orbital overlap isn't so good, as shown in this example, that bond is considered to be rather weak. And not only is angle strain an issue with cyclopropane, but so is torsional strain. If you look at the Newman projection for cyclopropane, you can see that these carbon-hydrogen bonds are pretty much eclipsing one another. And so again, that's going to give rise to significant torsional strain. And the carbon-carbon bond reflected in this part of our Newman projection, the carbon-carbon-carbon angle, there's going to be torsional strain between those two bonds as well. And so torsional strain and angle strain give rise to a very reactive cycloalkane. The three-membered ring, cyclopropane, is very reactive. And so when we use it as a reagent, we use it with caution. Now, cyclobutane, on the other hand, there is less angle strain than cyclopropane, and that is beneficial to its overall energy, as we saw in our graph, but there's actually a considerable more torsional strain associated with cyclobutane. So the neighboring carbon-hydrogen bonds, you can see they're all relatively parallel to one another. And so that interaction is going to be strongest when you have those carbon-hydrogen bonds, in a sense, eclipsing one another, being parallel in that manner. And so that's going to enhance the torsional strain associated with cyclobutane. Cyclobutane does adopt this non-planar, almost a puckered conformation to avoid and reduce some of the angle strain, but it can't really alleviate the torsional strain from that puckered geometry. Cyclopentane has much less angle strain than both cyclobutane and cyclopropane. It too, like the cyclobutane example, can adopt a puckered conformation. You see that one carbon is, in a sense, above the plane of the other carbons in that ring system. And that helps to reduce some of the torsional strain. So you can see that this carbon-hydrogen bond, the neighboring carbons, those hydrogens are not in the same, what we'll call axial position. They are not parallel to one another. Now, there is some possible interaction between these two axial hydrogens, and so that will result in some torsional strain. But nonetheless, it is a little bit less than what we observed for the cyclobutane, and so you can see that there's a significant reduction in the heat of combustion of cyclopentane relative to cyclobutane. Now, cyclohexane, as we saw in our graph, it adopts a conformation that really is almost virtually free of angle and torsional strain. And the most stable conformation of cyclohexane is what's known as the chair conformation. So we refer to it as the chair conformation in the sense that if you were to think of this part of the molecule, this plane, as being the seat, this is the head of the chair, and this would be the foot of the chair. And so that's where this term chair conformation comes from. But if we look specifically at the structure as shown, you can see that this carbon-hydrogen bond, which is referred to as being in the axial position, this vertical position, neighboring carbon-hydrogen bond is not in the same parallel orientation. It is in a opposite direction. You can see that it's below the plane of the ring, both here and here. So that significantly reduces the torsional strain. And even these carbon hydrogens, which are known, we call them the equatorial position, they are pointing in different directions, these two hydrogens here. And so there may be some torsional strain associated with this molecule as expected, but not significant in that they're completely overlapping. And so this gives rise to a very stable conformation for a cycloalkane. In addition, the angle strain is significantly reduced, that these carbons within the cyclohexane backbone, they can pretty much adopt the free tetrahedral angles of 109.5. Now, if we look at the Newman projection for cyclohexane, we can see that all the carbon-hydrogen bonds are staggered with respect to one another, which is a low energy conformation, as opposed to the eclipse conformation that we observed previously for some of our examples. So you can see that if we look down both these carbon-carbon bonds at the same time and draw the Newman projection for that perspective, we see that all these hydrogens are staggered with respect to one another. There's no overlapping carbon-hydrogen bonds on the front carbons. There's none of those bonds overlapping with carbon-hydrogen bonds on the carbons behind. So there's no eclipsing interactions. We see dihedral angles of 60 degrees for all the carbon-hydrogen bonds in front with those in back. And so this gives rise to a very stable ring system, which we again refer to as the chair conformation for cyclohexane. So let's look at the cyclohexane ring in a little bit more detail. So as you saw in the chair conformation where we explicitly showed all the carbon-hydrogen bonds around the ring, there are two positions in which those carbon-hydrogen bonds can take. There can be what's known as the axial position, in which the substituent is, in a sense, either straight up or straight down at a particular carbon. And there's the equatorial position, where the group, in a sense, is at the equator of that ring system. So if we treat in the ring as this being our plane, the axial position is up or maybe down, whereas the equatorial position lies around the equator of the ring. So to summarize, one group occupies the axial position, which is parallel to the vertical axis passing through the center of the ring, whereas the other group will occupy an equatorial position, which is positioned approximately along the equator of the ring, or the outside of the ring system. So it's really important to recognize that you have those two arrangements, if you will, of the groups at each carbon around the cyclohexane ring. And again, they're trying to adopt this tetrahedral. If you take a closer look at this particular line structure, you can see that to approximation, there is a tetrahedral-like arrangement of the bonds from that particular carbon. And so the axial and equatorial represent that arrangement of atoms in space with a relative angle close to the tetrahedral. But we will always see at each of the carbons in the ring both an axial and an equatorial position. And we'll show that more clearly on the next slide. So if we look at the cyclohexane ring in a little bit more detail, when we're drawing in our equatorial and axial bonds, here's an example where when we have our basic ring system, the axial bonds will be either up or down. And so when we're drawing them in around the ring, we start by drawing the first one up, the second one down, and we go up, down, all around the ring until we have this alternating pattern of axial bonds facing up, down, as we go around the ring. The equatorial bonds are also slightly up or slightly down as you go around the ring. And when we draw those in, you'll notice that this equatorial line is parallel to the lines that are one bond away. And so we would draw this equatorial bond facing in the same direction as this. Okay, so similarly, when we look at the next equatorial bond, it is parallel to this line and this line. And so this equatorial bond is parallel to carbon-carbon bond one bond away. So it's this line and this line that we would draw our equatorial in. For the purposes in our course, you'll most likely not have much of an opportunity to draw these ring systems, but it is important for you to identify the axial and equatorial positions on these cycloalkane ring systems, specifically the cyclohexane. So if you have any questions about cycloalkanes, by all means send me an email, or we can set up a Zoom appointment or start a discussion in our forum. Thank you.